Welcome everybody to this new webinar today dedicated on ceramic technologies and organized by our European Cluster of Ceramics located in Limoges. My name is Florine Boule and I'm director of the cluster. We organize this webinar every Tuesday and Thursday at 11 a.m. and 2 p.m. So these 2 days, this means 4 webinars per week, to learn more for you about our latest developments and products from our members. So a recommendation for you: when you log in, please enter your name or your email address so that we can identify you when you log in to compare with our registration file. So thank you for this. And before I leave the floor to Samuel, I would like to share with you the new dates of our B2B meeting, Ceramic Network, that will be held in Limoges the 4 and 5 of November. And this is a B2B meetings. There are also conferences on ceramics and technology, and also a visit of companies around Limoges. So if you are interested to attend as visitors or exhibitor, do not hesitate to contact us and write to us, or even go on our website and the website of the event, of course. So the webinar of today concerns PDC, Polymer-Derived Ceramics, and this is a small introduction of science and developments of PDC given by Samuel Bernard, who is researcher, Directeur de Recherche CNRS, at IRCER Lab, so Institute of Research for Ceramics in Limoges. And just a few words here about our next webinars that will be held in the next days. So go on our website here to consult every subject. If you are interested, do not hesitate to register. And before we start with the presentation, I give you some recommendation about the go-to meeting buttons. Please switch off the microphone and camera, also to have a better display speed and better broadcast also, and to avoid disturbing noises. And of course, if you have questions, please use the chat all along the presentation of Samuel. And you can ask your question even to the speaker, to the organizer, me, or to everyone. It depends on what you want. So you can ask your question, and I will read it at the end of the presentation so that Samuel can answer. So now I will share the screen of Samuel, and we can start the presentation.
Okay, so hello everybody. I hope you can hear me. So yes. First of all, okay, perfect. So I would like to thank Florine for your kind introduction, and especially I would like to thank the European Ceramic Cluster for the organization of this webinar. So as Florine said, I am Samuel Bernard, Director of Research at CNRS, based in Limoges at the Institute of Research on Ceramics. And I work with PDCs, I would say, since 20 years. This will be the topic of my webinar today. And in particular, I will speak about the past, the present, and the future of this particular class of advanced ceramics, after a brief introduction of our institute. So our institute, the Institute of Research on Ceramics, is located in Limoges, as you can see on this map, that represent all the institutes belonging to both the chemistry section of CNRS and universities. So this is our building, and so this institute is located in the north part of Limoges, where politicians decided several years ago to gather all the activity and research development dedicated to ceramics, going from training, the engineering school, as you can see here, and companies, as you can see, through research in our institute, and transfer, as you can see here, to transfer our knowledge from lab to industry. the Pôle Européen de la Céramique is located here. So our institute is composed of around 225 people, and we develop our research through 4 departments, as you can see here, with as a common objective the transformation of matter involved in the processing of ceramic. And these 4 research departments are closely connected to our characterization platform called Carmalim, in which I would say you can find everything to analyze and to characterize your ceramics. I would say except maybe solid-state NMR, but for this you can collaborate in France or in Europe. And the polymer-derived ceramics route belongs to the 4th axis. And in this group, we try to play with the chemistry of precursors to design polymer-derived ceramics, PDCs, through 3 types of materials, fibers and matrices, to design ceramic matrix composites, nanocomposites, and porous components in various systems, as you can see here: nitride, carbide, silicide, and boride. So let's move to the content of this webinar. There will be 3 sections, with the first one focus on an introduction to the polymer-derived ceramics approach. A second one describing 3 typical examples of PDCs, ceramic fibers, porous component, and dense ceramics. And a last one that will summarize this approach and that will give some ideas for the future. So let's move to the first section. So in 95, Professor Ralf Riedel from TU Darmstadt, Technical University of Darmstadt, reviewed the pre-ceramic routes and commented that the social route is the synthesis of oxide ceramics, while the PDCs route is largely applied for the preparation of non-oxide ceramics. So largely because, in fact, you can also prepare oxide PDCs like oxycarbide and oxynitride. So a flow diagram of the single steps involved in the production of PDCs is presented here. So the processing of PDCs via the pre-ceramic polymers usually occurs in atmosphere free of air and moisture, because you want to prepare non-oxide ceramics, and involve their synthesis from molecules commercially available or homemade, their cross-linking to increase their molecular weight, their semiization to transform the cross-linked polymer into an amorphous covalent PDCs, and an optional heat treatment achieving solution to occur at the end of the process to form crystalline polymer. So I would say that until now, the process is relatively close to conventional processing. But the main interest of this approach is that you can shape your polymer before the heat treatment using conventional shaping process, spinning, coating, pressing, injection molding, and to form a large range of ceramics after pyrolysis in the shape you have imposed at the polymer level. In parallel, you can shape the ceramic obtained by the direct pyrolysis of your polymer once prepared, and in particular in its amorphous state, as it is applied with the conventional way. However, this route is really interesting if the polymer-derived ceramic route can provide added value compared to the more conventional way. So we will see later how we can add value compared to the conventional way of preparing ceramics. So the precursor are the pressing polymers. They can be prepared as liquids, gel, solids, soluble, fusibles, or insoluble or infusible. The starting materials, the molecules, can be a monomer, which is thermolyzed, heat treatment at, I would say, between 50 degrees C to 400 degrees C to form your ceramic polymers. It can also react with a low molecular weight compound, is what we call chemical polymerization, as generally seen with organosilicon precursors. Dichlorosilane are considered as monomers, so they react with low molecular compound, as you can see, ammonia, to form pre-ceramic polymers, polysilane, for example, as a precursor of silicon nitride. But you can form a large range of polymer, polycarbocyanine, for example, a precursor of silicon carbide. So the molecule can be also a preformed polymer. You can consider this polymer as preformed polymer, and they can subsequently be cross-linked to form the ceramic polymers, the real precursor. They can react with a low molecular weight compound, chemical modification. So this is in general a chemical cross-linking. The preformed polymer can be mixed together, so you can mix a polysilane with a polycarbocyanine to form your ceramic polymers, or you can also modify your preformed polymer at micro and nanoscale. I mean, you can mix your polymer with powders, metallic powders or ceramic powders to form your ceramic polymers. So it means that the capabilities of this approach may offer to you significantly opportunities to engineer the ceramic polymers as precursor, enable their precise manipulation to shape them, then convert it to advanced ceramics with the shape which has been imposed at the polymer level, and usually with improved properties to be compared to conventional ceramics. So based on this discussion, we can establish some benefits of this approach. So your precursor and your polymer can be easily purified by distillation or crystallization. This means that the final materials will be highly pure. So it means you will control the stoichiometry at the polymer level. You have a good control of the physical state of your polymer, therefore you can tailor the rheological properties of your polymer just by changing the reaction conditions. So it means you have a high versatility in terms of processability to be shaped using established methods. As for organic polymers or plastic, as I mentioned previously, you can spin, you can coat your polymer, you can press your polymer, or use injection molding. So as I mentioned previously, you can control the composition of your ceramic at molecular scale because you start with precursor. So it means you have a high control of the structural homogeneity and the compositional homogeneity of your materials. And you can produce a large range of ceramics from binary system, silicon carbide, boron nitride, aluminum nitride, to multi-component materials made of 3, 4, or 5 elements. And you can also prepare hybrid materials. You mix your precursor with organic polymers, for example. And at the end, I will say that in general, you operate at temperatures lower than those applied in conventional processing. For example, to produce silicon carbide, you can prepare silicon carbide at 1000 degrees C from polymer. It will be amorphous. If you want to crystallize, you can reach a temperature of 1500 degrees C or 1800 degrees C, but this is still lower than the conventional process to prepare silicon carbide. So these advantages have been well demonstrated through the different studies which have been published since a while. In fact, this approach is not new. As you can see on this slide, although the first report of the synthesis and thermal decomposition of precursor have been proposed for the first time in 21, then in the 50s. In fact, the works proposed by Enger, Herbert, Chantrel, and Popper in the 60s are considered as a pioneer studies in the field of PDCs. Because in fact, the pressing polymers and the non-oxide ceramics which have been produced here have been characterized, which was not the case before. Then after these studies, so these fundamental works laid a decade later, in the 70s, to a demonstration that PDC can be prepared as fibers, silicon carbide, silicon nitride by Verbeck in Germany, and silicon carbide fibers by Yajima in Japan, and in particular through the chemistry of organosilicon precursor, I mean from polycarbosilane, polysiloxane, and polysilazane. And in fact, today, the production of silicon carbide fibers is found in industry, and it is based on the process published by Yajima in '76, so more than 40 years ago. So these works marked the industrial potential of PDCs. Then, in the 80s and 90s, there has been a worldwide activity in the polymer-derived ceramics field, in particular in Europe, Germany, France, in USA, and in Japan. These activities were focused on the design of ceramics other than silicon-based ceramics, I mean boron nitride, aluminum nitride, metal nitride, by these authors in particular. This period was focused on the extended activity on silicon-based ceramics, in particular in Germany, Japan, and France. It was also focused on a deep, in-depth understanding of the polycarboxyl and polysilane chemistry behind synthesis and their conversion into ceramics, silicon carbide, silicon nitride, mainly in France and Germany. A very interesting approach we will see later. Peter Greil from Germany, Erlangen, proposed an active filler control pyrolysis. He mixed pre-ceramic polymers with fillers, powders, in particular metallic powders, to reduce the volume shrinkage that occurs during the transformation of polymers into ceramics. So we will speak later about this potential. Then there was a very strong PDCs activity in Max Planck Institute in Stuttgart in Germany, especially on the SIBCN system proposed by Professor Riedel in 96 in the Nature journal. And some companies in Germany, Walkers, Clariant, in France, Ron Poulenc, in USA, Don Corning, emerged to produce at industrial scale polycarboxylane, Starfire system, for example, in US, and polysilazane, Clariant, now Merck, in Germany. Finally, since 2000, the activity is mainly focused on the design and development of the functionality of polymer-derived ceramics and on the structuration of the community. So the functionality was developed through the design of porous component, nanocomposite coatings, and the coupling of additive manufacturing with PDCs. The structuration of the community was done through the organization of symposia in an international conference, thanks to Professor Ralph Riedel, Professor Paolo Colombo, Professor Gian Domenico Soaru in particular. The writing of a large quantity of review papers, as you can see here, and the acceptance of European and worldwide PDCs focused project, as you can see here. And finally, during this period, we found some industrial academic partnerships because of the industrial potential of PDCs, particularly between Bosch and Technical University of Darmstadt on battery, between Merck and University of Bayreuth on coatings, between Safran Ceramics and our institute on CMC, for example. And today, the main activity of PDCs, I mean the synthesis, the manipulation of ceramic polymers, is concentrated in 3 zones of the world: Europe, American, and India and Asia. In Europe, mainly France, Germany, and Italy. In US and Brazil, and in India, of course, China works a lot on PDC, especially on fibers, and Japan with the Nagano Institute of Technology. However, it is required to collaborate with other groups in order to improve our understanding of PDCs. So, for example, in Europe, we work with experts in CMC, University of Bordeaux, University of Augsburg, expert in solid-state NMR, Sorbonne University, or expert in mechanical properties. In US, we work with people expert in computation or in thermochemistry, and in Japan with people expert in high pressure and in microscopy. So this is really necessary to fully understand the behavior of your PDCs. For example, in air atmosphere, for example. So these huge collaborations through the world mainly led to the application of PDC in different fields: environments, water treatment, gas permeation, energy, use as electrocatalysts in battery, fuel cell, supercapacitor, or use as catalyst, use also for thermoelectric properties or as solar absorber. In health, orthopedic mainly, as structural materials and as functional materials to develop, for example, the thermal conductivity and electrical conductivity. So now I hope you have a complete view of the PDCs, in particular their processing and application. And so I would like to introduce briefly 3 key examples of PDCs by starting with ceramic fibers. So as probably you know, ceramic fibers exist in 2 systems: oxide with as a reference silica and alumina fibers, and as non-oxide with silicon carbide as a reference. And as I mentioned earlier in my talk, these fibers, silicon carbide fibers, are prepared by the PDCs route. Here is a map of Professor Ishikawa published in 2016. So he reviewed the different types of silicon carbide based fibers, and you can see the different silicon carbide fibers that are industrially produced. So the cost of these fibers is quite expensive, from $1,500 per kilogram, I would say, for the lowest purity fibers, to more than $10,000 per kilogram for the highly pure silicon carbide fibers. So the PDCs process to fabricate these fibers is the same, whatever the fiber composition. Let's consider the example of SIBCN fibers we produce in our institute. You can recognize here the different steps of the PDCs process: the monomer, chemical modification with a low molecular weight compound, methylamine, to produce new precursor, the pre-ceramic polymer. Then shaping, we use spinning in the molten state. This is the best method to produce fibers through the PDCs process. So you form your polymer fiber, then your polymer fibers are cured and polarized to form your polarized fibers, I mean the ceramic fibers, in the SIBCN process. So I didn't mention about this curing process, which is in general applied just to produce fibers. It is essential to render your fibers infusible in order to avoid the collapse of your fiber during the further pyrolysis and heat treatment to more than 1000 degrees C. So the fabrication of these fibers is probably the most complex in the PDCs field, because you should produce a polymer that contains functional groups that offer to him fusibility, and you should stretch your fiber during the spinning to reduce the diameter of the fibers in order to reduce the quantity of defect in your fibers. Your polymer should be stable during the spinning with particular rheological properties, non-Newtonian, and a viscous component above the elastic one. Your polymer should be cross-linkable itself or with the atmosphere used during the curing, and it is expected to have a limited weight loss upon the pyrolysis. So, having such requirements in the same ceramic polymer is really challenging, and is why it is really complex to produce fibers through the PDCs process, but in fact, it is the only way to produce ceramic fibers. So you need, in fact, to work and to play with the chemistry of your ceramic polymer, and it is what we are doing in Limoges. Second example, the porous component. So I would say there are around 6 processes to develop the porosity of PDCs, mainly based on template-based process. Supercritical drying developed in University of Trento by Professor Gian Domenico Sowaro, and forming process developed by Professor Paolo Colombo from Padua in Italy also. So I will speak about 2 processes. First, I will speak about the hard template approach to develop the porosity of polymer-derived ceramics. Here is the process. So we use templates, mainly commercially available and mainly based on carbon. You can use active deep carbon, CMK3. You can use also silica, but the process differs a bit. And you can recognize here the different steps of the PDCs process. You start with organosilicon polymers as pre-ceramic polymers, which has been produced from monomer. You have your shaping process. It means it's an inclination process to infiltrate template. So it means that your polymer should be in a liquid state and or highly soluble. Then you have the pyrolysis. So your polymer should be cross-linkable to avoid the collapse of the porous structure during the pyrolysis, and especially during the template removal, which is a step that occurs after the pyrolysis, usually in air because you use template. So this means that you form porous PDCs as a replica of the template. Okay, so in fact, you can use different types of porosity, starting from mesoporous to macroporous porosity, and you can also form PDCs with a hierarchical porosity. And in fact, the porosity of your PDCs closely depend on the porosity of the template you use. If you use activated carbon as monolith, you form PDCs as monolith, which are mesoporous. So such materials can be used as catalyst support. So second example, a last example to design the porosity of PDC, the use of sacrificial agents. So again, you can recognize the different steps of the PDC strategy. You start with a preformed polymer commercially available, silicon carbide precursor, for example, polycarbocyanide. It is modified with a low molecular weight compound to add other elements, boron here. Then it is modified at microscale with PMMA spheres as sacrificial agent. So you form your precursor, which is a mixture between your preformed polymer modified at a molecular scale and PMMA. You can control the ratio between both compounds. That you press, this is a shaping process to form pieces, as you can see here, the yellow one, and you have a pyrolysis to transform your polymer into a ceramic. Why? The PMMA spheres disappear during the pyrolysis because they are decomposed, so they leave voids, and the voids are the pores of your materials. So the diameter of the pores depends on the diameter of the PMMA sphere. Here we use PMMA sphere with 25 microns in diameter, but you can see that we have an interconnected porosity. So it is clear that these materials can be used in dead end filtration as a membrane. You can change the shaping process. Instead of pressing, you use extrusion-based processing. And in that case, you can form capillaries. And such capillaries can be used as in closed flow filtration as a membrane. The last example, so the design of dense ceramics. So we start again with a preformed polymer, silicon carbide precursor. We don't care about the name, but this is a commercially available precursor. This precursor is thermally crossing to form your ceramic polymer. Shaping, warm pressing. The pressing is achieved at 300 degrees C, and pyrolysis at 1500 degrees C to form your PDCs object, here silicon carbide, because we use the silicon carbide preformed polymer. So you can again recognize the different steps of the PDCs process. But here you need to infiltrate several times your object with the preformed polymer to improve and increase the density of your materials. So this is a time-consuming process. Alternatively, you can use again the preformed polymer, a direct pyrolysis into silicon carbide powders, amorphous, then sintering by SPS here at 2100 degrees C to form your silicon carbide object with such properties, an hardness which is relatively high, more than 25 GPa. So in the introduction, I said that this strategy is really interesting only if the PDCs route offers added value compared to the conventional process starting from powders. And here I would say that is not really the case, because you still need to apply the very high temperature of sintering to densify your silicon carbide, as it is applied using conventional process. We know that boron is a sintering additive of silicon carbide. Therefore, in our group, we consider the same preformed polymer to be modified with a borane, a low molecular weight compound, to form a boron-modified polycarbonylate, which is a real pre-ceramic polymer. Then it is pyrolyzed at a certain temperature to form boron-containing silicon carbide powders to be sintered later. And because of the addition of boron at molecular scale, we can sinter these powders at a temperature as low as 1750 degrees C to form nearly dense silicon carbide object with a relatively high hardness, as you can see here, and an electrical conductivity which can be controlled through the amount of boron you use at molecular scale and the temperature of sintering. But just by adding boron in your polymer, you can significantly reduce the temperature of sintering of silicon carbide by 400 degrees C, which is not so bad. You can use the same strategy, changing the nature and the composition of your polymer. You can use polysilane. In that case, we add a titanium-containing precursor, titanium amide. The same process, we form our pre-ceramic polymers that can be directly pyrolyzed into powders to be sinters, and we form these colored pieces with an extremely high electrical conductivity because of the presence of titanium nitride nanoclusters, which are dispersed in a silicon nitride based matrix, as you can see on this XRD pattern. So here we form nanocomposite with a very high electrical conductivity, the highest of the PDCs materials. And these materials are very interesting because you can control also the color of your materials through the quantity of titanium nitride nanocluster you use in your materials. So let's finish the webinar with some conclusions and perspective. I hope that I convince you with the interest of the polymer-derived ceramics route. In fact, the polymer provide access to a large range of shaped ceramics using conventional shaping process, and to a large range of stable amorphous ceramics, and the optional high temperature precisation or the sintering, as you just saw previously, can provide access to materials which crystallize in situ, which provide macro or nano-sized composites. So this method has a great scope for further development because of the large flexibility in terms of polymer chemistry and processability. So it means that polymer-derived ceramic can be seen as providing a potential platform to create new properties for non-oxide advanced ceramics. And clearly these materials might make a high impact in the community. However, to reach their large applications, the chemistry must be simple. Sometimes it is really complex. I didn't mention this, but I think I mentioned, you work under finite atmosphere, argon, nitrogen, or reactive atmosphere, ammonia, but I mean without oxygen, because if you use oxygen, you form oxide. And this increases the cost of these materials. So for application, we should simplify the chemistry, and we should prepare polymers that can be stable in a short period in air. This is really possible, and this opens their application in industry. There is a key issue of PDCs. You can clearly see on this image. The volume shrinkage that occurs during the polymer to ceramic conversion. It usually represents more than 50%. So you should know this before preparing your materials. I would say that it can be significantly limited through the modification of your polymer at nano or micro scale, as I mentioned previously, using fillers. Passive fillers, like ceramic powders, you can mix your polymer with ceramic powders. Active fillers, with metallic powders, for example, and in that case, you'll considerably limit your shrinkage occurring during the transformation of your polymer into ceramics. And this modification enables the fabrication of a vast range of advanced ceramics to be applied in numerous engineering and specialized applications. This is well described in this slide. Finally, we know that the structure and the composition control the material properties. This is valuable for all advanced ceramics. So in the PDC strategy, an in-depth understanding of the polymer chemistry, ceramic conversion, microstructural functional properties correlation is needed. This will lead to the rational design of polymer-derived ceramics. And this means that you should collaborate with experts, with groups, experts in, for example, structural investigation, SOLICET NMR, for example, in thermodynamic investigations, in rheological properties, to measure the rheological properties of your polymer in order to control their shaping, and combined with computation and machine learning. This is really important to further understand the properties of your polymer-derived ceramics. So I would like to thank you for your kind attention. I would like also to thank all my group, because it is not only my work, it is a work of a group. And I would like to thank my group. I know they are here, and especially you for your kind attention. Thank you very much.
Thank you, Samuel, for your very interesting presentation. I have some questions to ask you in my private chat. So the first one is about the issue of the utilization of these PDC precursors for industry. Are there any problems that are withdrawn for industrial application?
Yeah, as I mentioned, the big problem is that you should use chemistry to prepare your polymer, but in fact, you can ask a startup or companies that produce ceramic polymers. But the main issue, I would say, is the use of oxygen-free atmospheres. So to transform your polymer into non-oxide ceramic, of course, you need to use argon in the case of carbide, ammonia in the case of nitride. So I would say that, and to manipulate your ceramic polymers, you need to use glove box. So I think it increases the cost of your materials, but at the end, this is a balance between the properties of your materials and the cost. If the properties of your PDCs are really above or significantly increased compared to conventional ceramics, I think it is not a problem. But there are some examples of industrial application of these PDCs, the fibers. This is a typical examples, but you can also find example in Germany. They produce coatings at industrial scales. There are some opportunities, but you need to simplify the chemistry of your materials and to know that you should work under oxygen-free atmospheres.
Okay, and what about 3D printing of these PDC materials? Is it possible to your knowledge?
Yeah, there are recent examples of the combination of additive manufacturing, stereolithography, robocasting, etc., of pre-ceramic polymers. So we have some projects on this topic. To be honest, I don't know if there will be an added value compared to conventional shaping processes, but we have projects and it seems that it works quite well. And we'll see in few months if the coupling of PDCs with additive manufacturing is interesting for industrial applications.
Okay, thank you. We have another question about the price. Polycarbocylane are very expensive. If we think on an industrial scale, can it be industrially feasible to prepare thick ceramics?
Okay, yeah, polycarbocylane are quite expensive. It is around $2,000 per kilogram. Because in fact, it is expensive because there is only one producer in US. Okay, maybe in China you have, but there is only one producer in US, so this is why this polymer is quite expensive. And if you can produce at lab scale, or if you can imagine a company as a concurrent of this US company, you can significantly reduce the price of this polycarbocylane. It is what occurs with polysilane. In fact, polysilane that are 10 times lower than polycarbocylane. Yes, the chemistry is simple, but yeah, if you have concurrent companies, you can really decrease the price of these precursors. So I think you can produce silicon carbide materials using this PDCs route at a relatively low cost if you can produce by yourself the polymer.
Okay, thank you for your answer. We have another question. Can you please give us an example for when you said the pre-ceramic polymers can be modified at micro nanoscale?
Yeah, in fact, as I mentioned, the polymer to ceramic conversion. So the conversion of the polymer involves a very large volume shrinkage. So the polymer are easily dissolved in solvent or meltable. So you can really mix your polymer with powders, nano powders, for example. We use titanium nano powders to be mixed with polycarbocylane. And we observed during the pyrolysis that titanium nanopowders reacted with your polymer to form titanium carbide phase in your material. And we considerably reduce the volume shrinkage of the polymer because of the reaction of metallic nanopowders with the polymer and with the atmosphere. And we can form PDCs with significantly limited volume shrinkage. I mean, you can even produce near net shape PDCs by the mixture between metallic powders or nanopowders and your pre-ceramic polys. It is the solution and the only way to control the volume shrinkage occurring during the transformation of your polymer into ceramics. And I have samples. I can send papers.
Okay, thank you. Another question, is there any limit in the selection of polymers to be combined with PDC? Can PDC be combined with phenolic resin?
Yes, you can mix your pre-ceramic polymers with resins, with organic polymers. I would say the limitation, it depends on the application. If you want to shape your polymer, yes, you should select a resin which can be homogeneously mixed with your polymer, and the mixture should be meltable or soluble or liquid to be shaped. So the limitation is not in terms of chemistry, I would say it is in terms of processing. What you want to produce starting from this mixture.
Okay, thank you. Another question about thickness of the pieces. Can we imagine to build thick pieces of ceramic with PDC, and is the debinding an issue in this case?
Okay, the thickness can be few millimeters, but we work with CTTC in particular several months ago, and we were able to produce PDCs with a thickness of more than 50 millimeters, and the diameter was 100 millimeters. So it worked quite well, but you need to control the chemistry of your ceramic polymers and to use fillers inside. But you can produce ceramic pieces with a controlled thickness from few millimeters, 1 or 2 millimeters, as some example I showed previously, to several centimeters. And we didn't observe any cracks, any defects of these materials after demolding.
So it works?
Yeah, it works quite well.
Another question about the process. Have you used the injection molding technique to shape PDCs? If yes, what was your important results? If not, would it be open to test?
Yeah, I never tested injection. In fact, it's not really an injection molding, but I know that it works. But in our lab, we didn't test it. We tested injection, but not injection molding, but I'm sure that it works. Yeah. We have some examples in the literature.
Okay, we have 2 other questions. Do you have examples of application of PDCs as thin layers?
Yeah, a lot. We have a lot of examples. In fact, with controlled thickness is not a problem. You can form very thick coatings and use as antibacterial applications. Or you can use also, you can really control the thickness. But as I mentioned previously, again, the issue is the volume shrinkage. You should control this volume shrinkage. If not, you can crack your coating, you can produce defects. So the main issue is the volume shrinkage. And usually to produce coatings, you mix with fillers.
And what kind of thickness do you have in this case for the thinnest thickness?
From few microns to several millimeters.
Okay, few microns are the thinner?
Yeah, I would say nanoscale. I think it's really difficult, but few microns, yeah.
Few microns are possible. And what are the applications or properties reached?
The applications is to protect the substrate against oxidation attack or against corrosion. You can also form membranes to filtrate as coating, to filtrate gas or to purify water. I have some examples also of application of coatings. Okay,
very interesting. And finally, do PDCs can be used as additives for traditional ceramic processes, sintering additives, for example?
Yeah, they can be used. Yeah, for sure.
Okay, and what kind of properties can you tune by using them?
You can develop the thermal conductivity, the electrical conductivity, the color of your materials, etc., etc.
Okay, so there are a wide range of application of these PDCs. And I think your presentation was very good in this sense, so that we can have more information, and we can have now the knowledge about the application and also the industrial application we can expect from this PDCs. So thank you very much, Samuel,
for
giving this presentation. To conclude, I would like to say that if some people are interested to have more information about PDCs, Samuel will send to you his presentation. So you can ask him directly if you have a question about some projects you are conducting on PDCs, or maybe if you want to ask the cluster if you would like to assist to a more longer presentation, more longer section, maybe we can organize it also. And even if you have other questions about ceramics, you can ask us, of course. So I would like to thank the speaker again.
Thank you.
And wish you a good day to everyone.
Okay, bye-bye.
Bye-bye.
Bye.